Hi, and welcome to the procedural part of the first lab, which is Archimedes' principle and buoyancy. And let me give you a tour of the equipment we have here. This is a Vernier Lab Pro interface that allows data to be taken and logged directly onto the computer. This is a scale that we'll be working with. This instrument here is called a force probe. It allows you to directly measure force. So remember from Archimedes' principle, the force acting on a scale is going to equal, assuming you're holding it vertically, is going to equal the weight of the sample minus the buoyant force, the upward buoyant force, which we're going to use to calculate the density of the aluminum sample. And so this is the aluminum sample right here. It's a cylinder. We will be measuring the dimensions of the cylinder and calculating its volume that way. We will also be calculating its mass. You see this scale here. That gives you the mass of the aluminum. So you're going to want to record that mass. You're going to use it to calculate the density a couple of different ways. So the first part of the experiment, if you look at the table, and so this is going to be in the lab manual. And so what we're going to do is gradually submerge the aluminum cylinder in water. And so we have this container of water. It doesn't measure volume directly, but you can see that it measures the height in millimeters. The diameter of this circular or the cylindrical container is 5.5 cylinders, plus or minus 0.1 cylinders. So you can calculate the volume by the height of the water displaced multiplied by the area. And if you know that the diameter is 5.5 centimeters, then you can figure out the radius from that, and you can calculate the cross-sectional area. And so once you have the cross-sectional area and you have the height that's displaced, that will give you the volume that's displaced. So you'll notice back at this table, you have a column for displaced volume. So again, the diameter of the cylindrical cup is 5.5 centimeters, excuse me. The height is going to be measured in millimeters. So I've got it set up so to start with, you're right at 5.5, or rather at 55 millimeters. So we're going to try to work in 5 millimeter increments and then see what the corresponding force reading is. So for now, we're going to go directly to Logger Pro. And so you notice it's giving a reading for the force. I've already calibrated this, but what you're going to need to do when you hold it down is you're going to need to, you notice it's not reading exactly 0. So what you're going to need to do is select 0, go to experiment, and you hit 0, and when you're holding it vertically, you're going to hold it vertically, and you notice you're reading very close to 0, and that's fine. So what we're going to do now, I'm going to put that down for a second, get everything set back up. What we're going to do now is suspend this, my finger's in the way. Suspend this, the aluminum cylinder from the vernier, and you notice you're getting a reading. And it's fluctuating a bit. So how do we deal with the fluctuation? Well, what we're going to do is we're going to click on collect. So I'm going to click on collect. And you notice we're getting a steady reading coming out, and it's taking about 10 seconds to get that reading. So what we're going to do then is once we have that reading, you're going to go to Analyze Statistics, and you notice the mean. It's 1.057. So you're going to have a mean of 1. And this is the force probe, so that's in newtons. So it's 1.057 newtons. And so that's the weight suspended in the air. And so now what we're going to do is, give me a couple of seconds. Now what we're going to do is start to submerge the cylinder in water. And so let's see if we can get this from 55 up to 60. So again, we've got it at about 5 centimeters. And so we're going to hold that as steady as we can. And we're going to hit collect again. So now the mean, when you look at it, is 0.9675. So that's how many newtons for 5 centimeters of displacement. And so now we're going to let this focus. All right, so it's at 55, so we want to get it to 65 and repeat the process. So again, we're doing calculations. And so that's 0.83, showing the reading, that's 0.8345. And again, that's newtons. So now we're going to go back. Let's get that. See if I can turn this a little bit. All right. So was it 55? We did 60. We did 65. Let's do 70. Okay. So we do 70. We click on this again. And the mean is 0.6983 newtons. So then we have it fully submerged. It reads about 72 millimeters in height. And we're not including the hook in the submergence. But now we have it 100% submerged. Oh, you have to be very careful not to touch the ground for this. We're going to redo that one. I'll add a little bit more water because I think that would help. So give me a couple of seconds to add a bit more water to this. Okay. So I apologize for the cramped conditions, but okay. Here's the scale. So you find the scale. Okay, so we're at about 65. And so when we submerge this fully, all right. So we have it fully submerged. And it's fully submerged at about 80. So it's a bit more than 15. So we're able to get 3 readings rather than 4. But we do the fully submerged. And again, it's going to take about 10 seconds. There's a little bit of fluctuation, but that's okay. And so the mean there is 0.6698 newtons. So that's the net force that you're getting. So that's the mass, or the weight of the object, which we measured, minus the buoyant force. So you go here, you've got the weight in air. You go back to this table, you've got the weight in air. And so then the weight in water, and where it says none, the weight in water is going to be the weight in the air for that reading. And you just work your way down. And then the displaced volume, remember we worked in 5 millimeter increments, but that's the height. To get the cross-sectional area, it's 5.5 centimeters diameter. So pi r squared gets you the cross-sectional area. So that'll get you a value for the displaced volume. So make sure you get those in SI units. Just make sure you identify the units and put them in. And then we go to the data for full immersion. So for this part, we're going to go back and forth between the weight in air and the weight in water. And we're going to do that 5 different times. So let's just make sure, first of all, that when we go back to Logger Pro, okay, so we're going to need to zero the force probe out. So go to Experiment, 0. All right, that didn't do it. All right, so you have the force reading 0 when it's hanging vertically with nothing suspended. So then we're basically going to dunk it a couple of times and take it out. So that's going to take a couple of minutes to do. But again, we're starting with water volume at about 65, and then it goes up to about 80. So and that's millimeters. So here, we hang it, and so you hit collect, give it 10 seconds to measure means. So the mean is 1.030. So you can see there's some variability in the measurements. That has to do with the force probe, but keep that in mind. So then we submerge fully. So here the mean is 0.6436 newtons. So again, the difference between the two is the buoyant force when it's completely submerged. And if you know the buoyant force when it's completely submerged, you can figure out the density of the object. Okay, so again, we do this a second time. Now keep in mind there might be some water still on the cylinder, so that might affect the results. The mean is 1.033 newtons. Submerge it, redo it. And so now it's 6.550 newtons. So we pull it out. Okay, so that's 1.025 newtons. And then submerged. And that's 0.6070 newtons. And so that's 1.032 newtons. Submerge it again. And that's 0.64449 newtons. And then one last run. Okay, so that's 1.028 newtons. And submerge it. And okay, so that's 0.6468 newtons. So again, the difference between suspended in air and suspended in water is the buoyant force. And if you know the buoyant force, you can figure out the density of the object in question. So we went over some examples like this in class. So the last thing we're going to do, once you have all that data, you're going to make a plot of the buoyant force versus the submerged volume. So obtain the slope and the uncertainty in the slope. And so those directions are in the content section on Blackboard. So what is the expected value of that graph? So that's the buoyant force versus the submerged volume. And you should have 3 measurements for that. And so what is the expected value? What is your percentage error? And don't be surprised if the percentage error is a little bit high. We only took 3 data points. But you're going to calculate the density of aluminum 3 different ways. The first is from Archimedes' principle. So you divide the buoyant force, which you can figure out, by the density of water times G. That gives the volume of the aluminum. And then the density is equal to the mass divided by that volume. And so we measured the mass right away. The second way is the densities, the measured mass divided by the displaced volume. The displaced volume is probably going to be a bit more approximate. It was about 15 millimeters, somewhere between 15 and 20 millimeters. So you have a pretty high uncertainty with that. And the third way is the measured mass divided by pi r squared times h. So what we're going to do is we're going to take a caliper. Calipers are more precise than regular measuring instruments. And we're going to measure the dimensions of the aluminum cylinder. Now, I'm not going to explain how to use the caliper if you've never seen it done, but what I'll do is I will give you the readings from this. So you squeeze it tight. You see, and this is the diameter. So the zero line's between 2.4 and 2.5 centimeters. So it's 2.4 something. And it looks like the marker corresponding to 7, if you look on the lower scale, most closely lines up with the mark above this. So that would be 2.47 centimeters as the diameter of the aluminum. And then we're going to measure the height. So this might be a bit more challenging. All right, I'm going to put this down for a second. Okay, so now I've got it around there. And so you look at the zero line. It's between 7.5 and 7.6 centimeters. And the line that lines up looks like 8. So it's 7.58 centimeters. So that's the height. And the previous number I gave, which I think was 2.47 centimeters, was the diameter. That gives you enough information to calculate the volume of the aluminum very precisely. It's going to be the most precise way to calculate the volume. And so in all three cases, you have 3 different values for the volume with 3 different uncertainties. The mass you know pretty well. And so you can use that to you can use that to get your density values. So you're going to look up the value for the density of aluminum in kilograms per cubic centimeter, or rather cubic meter, and compare that to what you get from these measurements. And so do the percent errors and do the error analysis. If you have any questions about uncertainties and error analysis, please do not hesitate to email me. Okay, so thank you for that, and I will see you next time.